So let's begin. We're going to take our problem. We're going to try and add vectors. We're going to try and do it graphically. And I've extracted the two vectors from the problem. Now that I've done so and taken them from the problem, I don't really need the whole problem there. So I'm going to clear out some space for us to work. Now, I think it's best, and I'll tell you that you will have more success if you, like I, draw as carefully and as measured as possible. But we're going to have to measure and deal with angles. So that's why you have a protractor. So I'm making myself a coordinate system because all this information is relative to our coordinate system. And so we need to use a coordinate system that we all agree upon will work for this problem. So here's my coordinate system. And it's going to have the normal trappings of north, and that's also positive, and east, and that's also positive, and south, and that's negative, and west, and that's negative. All right? Now what we have to do is draw in each vector and draw them one at a time. We represent vectors as arrows, so we're going to draw each arrow, but when we draw the first arrow, we're going to start here at the origin, and then every subsequent vector begins where the other vector leaves off. Does that make sense? So we draw one arrow, and then wherever the tip of that arrow is, the next arrow goes there. All good? But we have to be careful, and we have to be measured. We want to draw a 30-degree angle here, because our vector is 30 degrees north of west. This is where your protractor comes in. I'm going to put my protractor down so that the hole is right there at the origin. Careful. I'll try and get the baseline lined up as perfect as I can. Oh my word, Mr. Sheldon, stop that. I'm going to grab my pen and mark 30 degrees. All right, so I've made a mark. Now before you do anything else, we have to draw the vector, but the vector's length matters. We're trying to draw this to scale, but I don't have something that's 120 units long, but the velocity is 120 meters per second. But I need to create a scale then. One thing I'm going to notice is that the wind, and I did this on purpose, 4 times the wind is the plane. Do you notice that? So whatever scale I make, I just need to make sure that the plane is 4 times longer than the wind. So I'm going to choose something that's a multiple of 4 for my length. And it just so happens that for me, 4 inches is this long. I'm going to use 4 inches. That's for the plane. And then I can use 1 inch for the wind. Does that make sense? Now, you might want to use a different scale. Great. Use a scale that makes sense for you. Like 8 centimeters isn't bad either. And the advantage of using centimeters is that they're 10 divisions per thing. Inches are kind of a pain because they're halves and 5/8 and 16ths and stuff like that. So you may want to use a measuring system that works for you, but it doesn't matter as long as your wind is 4 times longer. As long as the plane is 4 times longer than the wind. Fair enough? I'm doing 4 inches. So I'll put my ruler down. I'm going to put 0 at the origin. There we go. I've drawn my first vector. This vector represents 30 degrees north of west and 120 meters per second. Okay, ready to go to the next part? All right, we have finished the first vector, so plane, check. Now I have to do the wind. So we're going to start where the plane left off. Now, the wind is just due north. However, remember, we're starting with a new origin here. This one's easy because it's due north, but if it was at any angle, you would need reference. So I'm putting my reference there. I'm putting a X and Y because it's a good idea to have reference marks for your next measurement, especially if the wind was like 45 degrees east of north. You would want some points of reference to take measurements for your angle. But as this is our first example, I'm taking it easy on you. Now, I want to be careful. I need to draw my wind so it's perfectly north, but I also want to make sure it's to scale. So I want to draw a 1 unit long wind. So I'm placing my ruler here. Careful. Bless you. There we go. 1 unit long. This is the wind. And it's 30 meters per second. All right, everybody caught up? We all good? We've got our 2 vectors together. Now, if you've been careful and you've been drawing them accurately, the result is a vector drawn from the origin to the tip of the last vector. That's your result. That will be the sum. That will represent the addition of 2 vectors. So I'm just going to draw a straight line. I would use your ruler for this. This is the actual answer. We want this angle and this length. This will be our answer. This is going to be the scaled graphical answer for our plane. Let's do the angle first, shall we? That involves using our protractor again. Using my protractor, putting the little hole on the origin and putting the line on the x-axis. I am between 40 and 41 degrees. What are you guys?
Same.
About the same? I'm going to put, I guess, 40. But you put whatever you measure. We all don't have to have the same answer here. We're doing this graphically, and there's going to be some differences in the way our measurements work out. That's the whole point. But I have to measure the length now. And my length is, so 4 1/2 and 1/8. So that's 4 5/8. All right, so I measured my length. Has everybody done the same thing? Now the problem is this. That's in inches, but that's not what I want, right? I want something in meters per second. So I want to convert it to meters per second. I got to use my scale to do so. Did you use a scale when you drew your arrows? For me, this arrow I drew to be 4 inches long. So my scale is 120 meters per second is equivalent to 4 inches. That's my scale. What'd you use for a scale? So what was the length of the airplane's vector? You need that. Because I'm going to set that equal to question mark, because I don't know the answer, but I'm comparing it to 4 5/8 inches. I'm using my ratio of my scale to figure out the scaled length of this vector. You guys see what I'm doing? We okay? Because now I need a calculator. I'm going to grab my handy dandy calculator. Alrighty, so 120 divided by 4, 4 5/8. I find that my question mark is 138.75, or I'm going to say 139 meters per second. Now, regardless of what scale you used, we should all be getting a number that's about the same. Plus or minus a couple is fine. It'll all depend on how careful you were with your measurements and how accurate you were when you drew your lines. But we've done it. We have added together our two vectors. We did it graphically, so now we have a result. The result is 139 meters per second at an angle of 40 degrees north of west. That's what we get when we added our two vectors together graphically. I don't know what yours are. Some of you, I'm concerned by the looks on your faces that you didn't do this. You shouldn't be writing down my numbers. You should be writing down what you measured. Pretty close, right? Not perfect, pretty close, not terrible. Now, doing the math is not necessarily harder, but for some of you, there are some complications, especially since it's going to involve trig. We have two vectors, the plane vector and the wind vector. I am trying to give you a place to start. I would encourage you to have a place to start, a place to hang the information that you have. That's why I'm going to write this down in a very specific way to give you a start. We know that the plane is 120 meters per second, 30 degrees north of west, and the wind is 30 meters per second to the north. Convert all vectors to rectangular, add together all like components, and convert our answers to polar. That's our process. So what I'm going to set up here is a quick chart. I want to convert these to rectangular, which means each one of them is going to have an x component and a y component. When I'm done doing that, I want to add these together to get a resultant that's in the x direction plus a part that's in the y direction. Once I finish that, although that is my answer technically, I have to express my answer in terms of a polar vector. 3 things to do. So I've created a chart to help me recognize what I need to do to finish this problem. I'll need to find 2 numbers here and 2 numbers here. I'll have to add those together so that I get the total in the x and the total in the y. And then when I'm done, I will need something with an angle. So let's start. Now, you guys are stingy with paper. Stop. Use the whole piece. Use a couple pieces. You want to be successful here? Draw things big and careful. You want to fail? Keep drawing little postage-sized pictures that you can't see anything. If you want to be successful, you want this to be something useful for you to use. I'm not going to worry too much about drawing out the wind. The wind is in one dimension, right? It's just due north. So I know that the wind is going to be 0 in the x direction plus 30 in the y direction. Right? I don't have to do any trig here. Right? It's due north. But for the plane, I'm going to have to do trig. So the first thing I'm going to do is give myself reference. I'm going to draw the plane. I'm going to use that reference to help me figure out the information about the plane. So the plane is 120 units long at an angle of 30 degrees north of west. So I'm drawing something for the plane that I can use to figure out its components. This is step 1, convert all vectors to rectangular. How do I do that? I start with drawing the vector out. Now, yesterday we went through this process. I said words like wrap a triangle around your angle. Do you remember that? Well, that's what we're going to do here. We're going to wrap a triangle around our angle. This triangle represents how much of the plane is flying to the west and how much of the plane is flying to the north. So I'm going to draw an arrow that traces along the cardinal direction first. So trace right there next to the angle. You want to do it this way. You want to wrap the triangle around the angle. And when you get to that point just below here, you want to stop and then put a perpendicular line upwards. You are forcing a right triangle with the right angle on the axis. We have wrapped a triangle around our angle. Do you guys see what I'm doing? Now, this part is in the x direction. This part's in the y direction. We are figuring out how much of the plane is moving in the x and how much is moving in the y. So, this part is the part where you're supposed to be good because you've been practicing. You have become excellent trig folks. You know that this is the opposite side, this is the adjacent side, and you can do your trig. And I'm going to time you, but I'm going to tell you how long it should take. Ready? Begin. All right, you should be done. If you're not, you need to practice the trig more. But I have 60 here and 103.9 here. These are the two vectors that define the plane's velocity. It's flying 103.9 to the west and 60 to the north. So now we have the sides of our triangle. We have to turn that into rectangular components. 103.9 is in the negative direction, so 103.9 in the negative x direction. And that 60, that's in the positive y direction. Everybody good? All right, we are done with that picture now. We go on to step 2, which is add our vectors together. So 103.9 plus 0, negative 103.9 in the x direction. 60 and 30, 90. This is the actual plane's velocity. But it's in rectangular, not polar. So we're not done, but we're close to done. But we have to do the last step now, which is convert my answer to polar. Again, don't be stingy with the paper. Draw something that will help you solve your problem. I'm going to draw something that will help me solve my problem, and I am intentionally not drawing it over here on this one. I don't want to use this one again. This got me what I needed, but don't muck it up with a whole bunch of extra stuff. Start nice and fresh so you have a nice clean space to work. Now, the part of that is because I want to follow these instructions. We didn't do this yesterday, so I want to follow these instructions. I think this one's easier. It says go 103.9 in the x direction. I'm sorry, negative x direction. Then turn and go 90 in the y direction. Right? Those instructions are very clear, aren't they? So drawing this should not be hard. It should be very clear. It's giving you the two sides of the triangle. And draw them just like this, one after the other. The plane actually is doing that. That's the result. Complete the triangle by starting at the origin and going to the tip of the last vector. It should create a right triangle where you can find the angle and the length. Again, back to trig. Now I'm going to use the Pythagorean theorem here. Why wouldn't I? It's easy. So r squared equals 90 squared plus 103.9 squared. You do you. You need the angle and you need r. I worked out Pythagoras and I found that r is equal to 137 with some change. And I'm going to use the tangent function because this is opposite and this is adjacent. And I know tangent goes with opposite and adjacent. So tangent theta equals 90 over 103.9. I know I told you to put all the trig functions, but you should be able to start cutting some corners soon enough. So I need the angle, tangent will give it to me. And when I do that, I get that the angle is 41 degrees. 40 and some change, but it rounds up to 41. So I'm going to bring my answer together. I have the length of my vector, and I have the angle of my vector, and I know which quadrant it's in. So I can say that my answer is 137 meters per second at an angle of 41 degrees north of west. So the plane actually is traveling faster than the engines think it is relative to the ground. Right? The engines think it's going 120, but the wind's helping it or pushing it off course. Hard to know. Now, how close was this to our graphical version? I think this is pretty good.